what we have seen so far is used both for inner and outer loop parallelization, namely to compute something called a dependence matrix. We have seen how to compute it for one dependence vector with a distance between two iterations that have a dependence. Okay, and all these dependencies, they are really a set of dependencies, since if the dependence vector for a pair of matrices, matrix A happens to be the same as the same dependence distance for another pair of dependencies, another dependence between for a matrix B, then we only need one of them, of course, since we really want to constrain how the iterations can be executed. So this dependence matrix has no knowledge really about which variables are causing the dependencies. It just expresses which iterations have dependencies, and there can be several variables that cause the same dependence. I mean the same constraint on the execution. Okay, so this set is it's represented as a matrix because that's the most convenient to manipulate. But since it's really a set, we must keep in mind that it's fine to change the rows of this matrix. I mean, we can put the rows in any order since they have no significance. Okay, so both inner and outer loop parallelization use this dependence matrix, and from the dependence matrix we want to find the first thing so say this dependence matrix, we can write it as D, and there is one column for each loop nest. So say the loop, all the dependencies are in the J or K loops. Well, they can be like this, for instance. Doesn't matter. But what we can see here is that there were no dependencies in the I loop. That means the compiler can be happy with the loops as they are and simply let the outer loop with I be run in parallel. Okay, so then there is no need for any iteration, for any transformation of the loop iterations. But it's not always so nice. Instead, there may be some non-zero somewhere here. And then it's not possible to run this outer loop in parallel, and we must try to find a loop transformation that will create a new loop, du. The loop is determined by this transformation that has zeros only here, and here something else, but all of them should be greater than or equal to 1. Well, to 0 actually, since it's fine. It's okay if they are 0, but okay, they should not be negative. The first non-zero of a row should not be negative. Okay. So now we come to expressing the transformation as a unimodular matrix. And we will next see, we will on this slide see why we want the transformation to be a unimodular matrix. The U is used to essentially enumerate all the iterations in a different order. Okay, and that is done with new loop index variables. But to find the loop bounds of this new loop, we need to compute the inverse of this. Okay, so therefore it should be a unimodular matrix. Okay, so why do we want to compute the inverse? We have this from the beginning. This is the original loop. And with the new loop, they are connected like this. So I is k times the inverse of u. We can insert I here. And then we get, that's why we use the inverse of u. And then, so we insert them here. And now we can simply solve for these variables, k1, k2, etc. from this vector, starting with the outermost, of course, since we must have the outermost loop with constant lower and upper bounds. Okay, so when we have found the bounds for k1, we can find the bounds for k2, etc. Okay, and then now we have not yet said how we will find this u that will, not that u, but the inverse of that will make our transformation useful. But we will see that soon. But when we have found it, we need to modify the source code, so to speak, to use the k variables instead. And what we could do, which would be terribly inefficient, would be to compute the I vector by taking the current values of the loop variables in the k loop nest and multiplying this, so that we would recompute the original loop index variables, and then we can use them to get the data, either to read it or to write it. That would be very wasteful of clock cycles. So what we instead do is to let the compiler compute the new, the array reference is expressed as the loop variables times a matrix plus a vector. So we will compute a new matrix like this. And that can be done at compile time. So what is really extremely nice when we have represented a loop transformation like this is that the complete transformation of the loop nest is expressed as a matrix and its inverse, and we can generate the new loop nest very easily from this transformation. Okay, so all the distances that come from the solutions to the dependencies, they are, as I mentioned, a set, but we express them as a matrix. Okay, and now the question is, what do these dependencies look like when we have used the transformation matrix? Because if a new, we have first we have D, and then we have well, okay, we have D, and then we compute new loop iteration order. So we get the new dependencies, and they are the old distance matrix times the transformation matrix. And if any row here in this matrix would have a leading non-zero that is negative, like this, for instance, say it's just one, we can have, it should be zero, but something like that. If there is any negative leading non-zero, it means the compiler is broken, because it has created a new loop nest that executes the iterations in the wrong order. Okay. So initially the dependence distance between two iterations was this, and now we have these index vectors instead, so we can see the distance between them, and it is exactly this. Okay, so we can actually, we don't have to check if we trust the compiler implementation that they are always zero in the beginning, but it's probably a good idea, well, it is a good idea to check that there is no bug which would create a negative leading non-zero element here. Okay, as a safety check, consistency check. Okay, so here is an example. This one is invalid.